So we're in section, today is 7.1, and we're going to talk about 0 and negative exponents. So first semester was we talked mostly about lines and equations that have to do with lines. Second semester, we're going to talk about things that don't always have to do with lines. So a couple of reminders and some vocabulary to start. An exponent exponents mean multiply. So for example, 2 to the third. This is telling us to multiply 2 by itself 3 times. So this means 2 times 2 times 2. And 2 times 2 times 2 is 8. So this is the exponent. The number 2 here in this case is the base. And the whole thing together we call a power. And we could pronounce this 2 to the third power. And a lot of times we just shorten it to 2 to the third. Or in this, with 3, a lot of times we'll say 2 cubed. And that reminds me, do you know why? Did I tell this one before? When Goldilocks was in the 3 Bears house, she wouldn't drink the glass of water that had 8 pieces of ice in it because it was 2 cubed. 2 cubed is 8 cubes of ice. That's for those of you that missed math joke / Friday.
I wish you were still missing them.
All right, so what we wanted to look at today is what does it mean when we have a 0 exponent? What is that telling us? And what does it mean when we have a negative exponent? So we're going to look at a pattern. We're going to make a pattern with exponents. And we'll use powers of 2. So 2 to the 4th. Well, 2 to the 4th means 2 times 2 times 2 times 2, which is 16. And 2 to the 3rd we said was 2 times 2 times 2, which is 8. And here we have 2, the next one would be 2 squared, which is 2 times 2, which is 4. Now, as our exponent goes down by 1 here, what are we doing to these numbers? What's the pattern here? What do we do to 16 to get 8? What do we do to 8 to get 4? We're dividing by 2 each time. So let's keep going. 2 to the 1 means 2, which is 2. We're dividing by 2. And now we get to 2 to the 0. Well, what happens when we divide 2 by 2? We get 1. 2 to the 0 is 1. Now let's keep going. 2 to the negative 1. We're going down in exponents each time. Well, what happens if I continue the pattern, divide by 2? What do I get when I divide 1 by 2? I get 1/2. Two to the negative 2, if I divide 1/2 by 2, half of a half is 1/4. And I can think of this as 1 over 2 to the first power. And this is 1 over 2 squared. And I could keep going. So we're going to use this pattern to make our rules. When we raise something to the 0 power, we get 1. And when we have a negative exponent, we end up with a fraction. All right, so we good? Everybody see what we did with this pattern? Yes?
Is it when you use like any number?
We could do this with any number, because we could say, I could go over here. I'll just write another one up here. 10 to the 4th is 10 times 10 times 10, which is 10,000. 10 to the 3rd is 1,000. 10 times 10 times 10. 10 squared is 100. 10 times 10. I'm dividing by 10 each time. Ten to the first is 10. And when I divide 10 by 10, 10 to the 0 is going to be 1. 10 to the negative 1 is 1/10. And we could do that with any number. That was a very good question. And we could keep going with the same pattern with 10. All right, so we're going to use that for our rule. So these are our 0 exponent and our negative exponent rule. Our 0 exponent rule. Any number to the 0 power is 1. Any number to the 0 power is 1. And the way we'd write that in symbols is a to the 0 is 1 for any number a. But I'm going to make one exception. A cannot be 0. Because 0 to the 0 gives us problems. You'll talk about that later in calculus. But we don't do 0 to the 0. Just like we don't divide by 0, we don't do 0 to the 0 power. So any number except 0 to the 0 power is 1. So doesn't matter what that number is. 2 to the 0 we saw was 1. Negative 4 to the 0 is 1. 5.76 to the 0 is 1. 1/352nd to the 0 is 1. X to the 0 is 1. Anything that we raise to the 0 power, as long as this thing is not 0, which we won't run into here, is 1. So that's a nice rule when it's always that way. Any number to the 0 power is 1. Always. Our negative exponent rule. Negative exponent rule is also very easy. Something that always happens. I like to say it this way. Negative exponent on top. We could also say in the numerator becomes a positive exponent on the bottom. So, and the way we'd write that in symbols is a to the minus n equals 1 over a to the n. We take the exponent and make it positive in the bottom of the fraction. So, for example, 2 to the negative 3 is 1 over 2 to the third. We make a negative exponent into a positive exponent on bottom. And this is the same as 1/8. 2 times 2 times 2 is 8. Negative 5 to the negative 2 is 1 over negative 5 squared. I turn this into a fraction with a positive exponent on the bottom. And this is the same as 1/25. Negative 5 times negative 5 is 25. I also have a part 2 of the negative exponent rule. The part 2 is a negative exponent on the bottom becomes a positive exponent in the top. So, for example, 1 over 3 to the negative 2. I have a negative exponent in the bottom of the fraction. We turn that into a positive exponent on the top. And I can think of this as 3 squared over 1. Which is 9. 1 over negative 2 to the third is negative 2 to the third. I can think of that as over 1. And negative 2 to the third is negative 2 times negative 2 times negative 2, which is negative 8. And I'm going to say do it with a variable. 1 over x to the negative 5 is the same as x to the 5th over 1. And that's just the same as x to the 5th. So our negative exponent rules just tell us if the negative exponent's on top, we move it to the bottom, make it positive. If our negative exponent's on the bottom, we make it positive and move it to the top. Yes?
On the side there, when it's like the parentheses with the negative 2, how do you get negative 8 if they're all?
Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. Now, if it was an even power, then we'd always end up with a positive, but with odd powers, we can end up with a negative. All right, so our homework with this section, the problems we have to do, all have to do with practicing on simplifying these things with exponents. So I just want to look at a few examples of simplifying these expressions that have exponents that have a zero exponent or a positive exponent. So most of your homework will say simplify or rewrite this expression. So we're simplifying. 6 to the negative 2. So I think to myself, well, I have a negative exponent. That means I need to turn this into a positive exponent in the denominator. And if it helps you to think of this, you can think of this as 6 to the negative 2 over 1. And we're going to flip it. 1 over, and we make the exponent positive. 6 squared. And 6 squared is 6 times 6, which is 36. Negative 9.3 to the 0. When we have a 0 exponent, that's like a gift. That's a gimme. Anything to the 0 power is 1. When we have variables in our expression, simplify means we want all positive exponents. So we want all our exponents to be positive. So we might see something like this. 3x to the negative 2, y to the 5th. And we want to simplify that. Well, I don't want this negative exponent here. So I'm going to say this is 3y to the 5th. And I need a positive exponent in the bottom. So I'm going to write that as 3y to the 5th over x squared. I take this negative exponent and make it positive in the bottom of the fraction. And I can't do anything else with this, so we just leave it written like that. Are we good there? 3 to the negative 2 over n. Well, I don't want that negative exponent there, so I'm going to move this to the bottom. So I'm going to write this as 1 over 3 squared times n. And 3 squared is 9. So that's going to be 1 over 9n. If I have 1 over x to the negative 7, I don't want that negative exponent in the denominator. So I write that as x to the 7th. I can think of this as x to the 7th over 1, which is the same as x to the 7th. Yes? So bring the 3 and negative 2 down, and how would you write it then? How you're thinking?
With the other ones that I see you do, they kind of flipped, but you just put 3 and negative 2 in there. That would make the negative 2 positive.
Yes. Yeah, you can think about it that way. That's just kind of a different way of thinking about what we did. That works as well. 7x 0. This is a more complicated one. T to the negative 5 over 2 to the negative 1 m squared. So when I look at these, I think, well, the ones that I need to deal with are the zeros and the negatives. So let's do it one at a time. What's x to the 0 power? 1. Anything to the 0 power is 1. So that's 7 times 1 times t to the negative 5, 2 to the negative 1, m squared. Well, 7 times 1 is just 7. What am I going to do with this t to the negative 5? I don't want that negative exponent, so what do I do with that t to the negative 5?
Make it positive.
Make a positive and put it on the bottom. So on the bottom, I'm going to have 2 to the negative 1 m squared t to the 5th. So I took care of that t to the negative 5. Now I have this 2 to the negative 1. What am I going to do with that 2 to the negative 1? I want to move it to the top and make that negative 1 positive. So this is going to be 7 times 2 to the 1 over m squared t to the 5th. What's 2 to the first power? 2 to the first power just means 2. And 7 times 2 is 14. So we'd have 14 over m squared t to the 5th. So turn x to the 0 into 1. T to the minus 5, we made it t to the 5th in the bottom. 2 to the negative 1 in the bottom, we made it 2 to the positive 1 in the top. And then we multiplied 7 times 2. Now as you get better at this, you kind of combine some steps, but I just did this one step at a time. All right, questions on those examples? All right, let's look at a word problem, and that'll be our last example. So, exponents describe population. A lot of population problems have to do with, population problems have to do with exponents. So we have a population of something that doubles every 8 years. If you listen to reports about COVID, for example, they talk about how quickly the number of cases double. And when it doubles more quickly, that means things are going worse. When it doubles less quickly, things are going better. So we can model the population. Let's say we model the population is 6,400 times 2 to the t, where t is an 8-year period. So every 8 years, our population doubles. The first question is, what is the population when t equals 0? Well, let's plug that in. Our population is 6,400 times 2 to the 0. Well, what's 2 to the 0? 1. So that's 6,400 times 1, which is just 6,400. What is P when T equals 2? Well, we plug that in. Population is 6,400 times 2 to the second power, or 2 squared. What's 2 times 2? 2 times 2 is 4. 6,400 times 4, which is, what does that come out to? $25,256,000. Well, what are we talking about when the population when T equals 0? That's a starting population. This is the beginning or starting population. When T equals 0, that means how many of these, whatever these things are, do we start with? After 0 8-month periods. Well, what about this when T equals 2? What is that telling us? The population after how long? 2 8-month periods, or 16 months, or year periods, 16 years. This is the population. After 16 years, 2 8-year periods. So sometimes you'll get these problems that say, plug these things in and interpret the results. Interpret the results here means that when T equals 0, that's the population we're starting with. When T equals 2, that's 2 16-year periods, which would be 16 years. All right, questions on our 0 or negative exponent rules? Anything to the 0 power is 1. Negative exponent on top, make it a positive exponent on the bottom. Negative exponent on the bottom, make it a positive exponent on top. Those are our 3 main ideas for today. All right, so our homework, our assignment. This is section 7.1. Oh, not even, sorry. Every other even. So that would be like 10, 14, 18, etc. Every other even. All right, there we go. Tomorrow we'll learn a couple more exponent rules. Wednesday we'll have kind of an extra practice / review day. And then Friday we'll have a catch-up day.